Hello and welcome to episode 3 of lecture 4 on systems inquiry. We will finish this episode 3 with an interview. So thank you, Professor Lopez, for giving us these 2 episodes of the lecture on systems inquiry. I would like to start the interview with the focus on systems thinking in general. Could you give a short overview over the terms used in systems thinking, like maybe elements or relations? What do they mean for systems? And then maybe also clarify how you differentiate between systems thinking and systems philosophy, because that I found really interesting that you use these different terms.
Thank you very much. That's a very good question. Well, systems thinking, I think, is what characterizes systems thinking mostly is an emphasis on process and relationships, as opposed to, let's say, I mentioned here, mechanistic thinking, which the focus is on things, objects. Although in traditional thinking, we assume that objects also relate to each other, but from a systems thinking perspective, relationship is primary. Mm-hmm. Let's say that even objects themselves are made of internal relationships. So systems thinking has this perspective of seeing the entire universe, reality itself, as a process in which everything is connected and relating to each other. So now the field of systems thinking is divided in 3 different subjects. One is systems philosophy. The other one is, which I just talked briefly, systems methodology. And the third field, subfield of systems thinking is systems practice. So from this perspective, although I mentioned a little bit about systems philosophy and systems methodology, systems practice is, let's say, a civic ecology practice, because civic ecology is essentially a systems thinking perspective.
Okay, so is the philosophic level, let's say, above the others?
Philosophically, what systems thinking does is try to discuss things like the nature of reality, what is reality, so the ontology. And then also what can be known and how can we know things, and then the systems epistemology. So I would say that system philosophy is more concerned about these philosophical aspects, the ontology, the nature of reality, what reality is about, and also about what can be known about that reality and the different methods of knowing. So the connection between systems philosophy and systems practice is because systems practice is basically based on the methodology that emerges out of the systems epistemology. So I would say that systems philosophy is basic.
Okay.
It is the foundation for systems thinking. And the methods are developed according to that philosophy. But I have to also mention that the understanding and the level of embracing systems philosophy by different systems thinkers varies. So some more academically oriented, more theoretically oriented systems thinkers, they really like to go deeper into the systems philosophy aspects. But I have met systems practitioners who didn't know much about systems philosophy, although they were using methods that were derived basically on conceptual systems philosophy.
It might depend on which discipline they come from, if they're natural scientists or social scientists.
Yes. Also, I think from a systems thinking perspective, the boundaries tend to dissolve. Mm-hmm. Because when you read, work by social scientists and work by natural scientists, they basically start using the same language. That's why I think another great advantage of systems thinking is to provide that interdisciplinary field where experts from different fields, like yourself in the field of business, sustainability, could talk to a more ecologically oriented person if you both come and use that language, the systems language.
Yeah.
So systems thinking has this great property of accommodating different fields. It provides a language that, in my view, facilitates the communication and the interdisciplinary collaboration.
You draw the distinction between systems thinking and then the positivist and the reductionist thinking. Could you maybe explain that in a few words for those who don't know about these concepts?
Right, good. Okay, so reductionist thinking is a main idea in mainstream science and is based on the belief that in order to understand a system, I can break that system into parts and then try to understand the parts in great detail. And once I have the understanding of the parts, then I can bring them together and have something, some type of understanding about the system. But according to systems thinking, this is not possible. Because as I mentioned in the lecture, one of the characteristic properties of systems thinking is emergence. And emergent properties are phenomena, are properties that emerge only in relationship. When we break down the system into parts, we miss those properties. And this is also, we also can say, if you admit that, if you accept that from a systems perspective, the whole is always greater than the parts. So it's almost, it becomes very difficult to build or understand the dynamics of the whole based on the dynamics of the understanding of the dynamic of the parts. But I'm not saying, because one problem that systems thinkers face with is to set the boundaries of the system. So the boundaries are always defined by convention and by understanding among the different researchers and thinkers involved in the process. And of course, depending on the scope, the scale of the problems, it becomes very, very difficult to understand all the relationships and connections involved. So in this sense, there is a tendency to simplify, but not in the sense of reductionism, because if I simplify the system by defining the boundaries which make the systems simpler, I'm still focused on relationships and interaction within that simpler system. So the focus, the goal is still the same, although I try to simplify the system by defining its boundaries. Positivist is a philosopher of science that believes that the only valid knowledge, truth, comes out of reason, logic, and mathematics. So as a branch, as a philosopher of science that was adopted very strongly in the beginning of science, but has been abandoned more recently by other scientists. In other words, systems thinking is assuming that there are other ways of understanding. For example, things like emotions, fears, some quality that make us humans very difficult to understand from a quantitative perspective. So positivist science, again, is that branch of philosophy of science that believes that the only valid form of knowledge is the form of knowledge that comes out of the scientific method.
Okay, so now that we're in the definition, maybe we can also define the holistic systems. You were talking about holistic systems. I would like to ask you to define what a holistic system actually is, and then maybe you can also answer the question that I asked myself, isn't everything part of a holistic system?
Yes, everything is part of a holistic system. I think the idea of holism and holistic systems has been around for a while. But I think the contribution of systems thinking to the idea of holism as this notion of relationship, relational view. Because in all forms of holism, there was a tendency of focus entirely on the whole and giving low value or importance to the parts. So the focus was on the collective and very little emphasis on the individual. I think systems thinking kind of solves this tension between individuality, the part, and the whole. Of course, and how that is done, because as I said, the system has this dual nature. a system is in itself a whole, so therefore it's relevant. But at the same time, is always a part of a bigger whole. So this relational view of holism, to me, resolves a tension that has been a problem in the past between individuality and collective, the part and the whole.
So we have within the Holland the systems which we then can we can look at the objects within the systems which are against systems and all the relations which are within it. I think this could become really complicated. So what I asked myself is, do we actually, if we want to understand complex systems in a bigger scale, do we need a different worldview to manage to handle this?
Well, I would say not necessarily, because again, as I try to explain, from a systems thinking perspective, the philosophical view of system, which is the systems worldview, provides the foundation. But you can become familiar with systems method without necessarily need to think in terms of systems worldview. As long as anybody in the world takes as the main focus of his or her study linkages between things, relationships, I would say that they are studying living system, complex system, or using systems approach. They may not necessarily have a view of reality that shares some commonality with the systems philosophy, but if the focus is on relationships and linkages, then I would say, yes, you are using a systems thinking approach to study a system. One thing I want to finish about the holism, I think another interesting difference between holism as previously defined and the systems thinking is that I think even in the mechanistic system there is a notion of holism, but in the mechanistic system they conceive the world, reality, the universe as a space populated by objects, discrete objects. So for them, each object is an entity as a whole in itself. So it's a different view, because for systems thinking, the whole is made by this network, is like a web. So the system is seen as a web, of interconnected things. So everything is like a little node, a little in a fishnet, for example.
Yep.
So it's a little different.
Okay. So then in your lecture, you also mentioned the topic of sustainability, which is, we sometimes forget that during the lecture, which is the big topic of the whole course with the civic ecology for sustainability. And then you showed that picture with the three systems, with the ecological system, the economic system, and the social system. But aren't within these systems other systems which could overlap the borders? So are they really borders, or are they strict?
No, not borders. I just, the idea here is to emphasize this nestedness. Because I said, according to systems philosophy, systems thinking, everything that exists is a system in itself, is a part or a whole in itself, and is always nested within something else bigger than it. So as usually in the discussion of sustainability, always comes this idea of the environment, the society, and the economic system. Yeah. So there are different ways of conceptualizing this. And for example, even if in modern industrial world they would take that nested system approach into consideration, probably they would draw that figure a little bit different. And they perhaps would consider that the economic system, because if they don't admit that, at least is the way they act, that the economic system is the primary system, and within that there is the environment, and within the environment there is society. The other system that I show now, other way of related sustainability, still considering the three, is to develop the tour circles. And then there is a problem with that, because I believe also economists probably would make the economic system circle maybe bigger than the other two. To me, the logic about the nested system is to think about, can we have society without economics? The answer is yes, because primitive human communities didn't have any economics. So, but can economics live without society? No. Secondly, can we have nature without society? The answer is yes. Can we have society without nature? No. So that's why I'm saying that the largest circle is the environment, in which the society is a subset of it. There is no way that we can have a society without having an environment. So that is the idea. The boundaries there just are not relevant. I don't know, because depends. If you define that environment, you can have in mind the boundary here for the environment is the region where my community, a society is located, where this little trade, this business taking place. But you could say, well, actually, the environment for me is the entire country, so the thing expands, and go all the way to say the environment for me is the entire nature. So where is that boundary of nature?
And then you, as an object, are also part of different systems.
Exactly.
Yeah.
And again, the boundaries, where it is, always to me is defined as a function of the question being asked.
Okay.
Okay, the problem that is being studied. Maybe the problem that is the focus of your study has planetary implications. So in that case, the boundaries should involve the entire planet. But maybe the problem being investigated is a problem pretty much located at the regional level. Although I'm not saying here that there is no influence. But as I said, boundaries are always arbitrary. And you have to define those boundaries according to the question being asked, and also in a way that can be studied. Because if the boundaries are defined in a way that the system becomes too complex, then it cannot be investigated.
Yeah, that would be, that might look good, but it's not handleable.
Not handleable.
Yeah.
But systems thinking offers this as, again, the driving force here is relationships. So as long as you are looking at linkages, even between two things, so two objects, if you are study how they interact, that is the driving force. Okay. The embeddedness of that, again, depends on a number of things. Question asks how much resources you have, expertise, how big is your group. Yeah. As the system becomes big and big and bigger, more and more complex, more different types of knowledge have to be engaged.
And this relational thinking, that's an issue I would like to ask you another question on. You were talking about evolution, that all systems evolve, always evolve, and you also mentioned the concept of co-evolution. So we always hear about evolution, then we hear co-evolution. Is it actually the same, or is there evolution without co-evolution? That is kind of confusing.
Well, for me, all evolution is co-evolution, but in the initial ideas discussed by evolutionists, I think the problem is they didn't call co-evolution because they always thought the environment to be bigger. And in organism, the ability of the organism to survive would be the ability, capacity of that organism to adapt to the change in the environment to be able to survive. But one thing that was not mentioned, which makes that type of evolution different from co-evolution, is that the effort of the organism to adapt influenced the environment itself. So it was only one-way direction. The big environment background changing, the organism is struggling to survive and try to adapt. This happens. But in co-evolution, that struggle to adapt to the change in the bigger environment also affects the environment.
So they affect each other.
Each other.
Yeah.
So that's why, I think more and more this notion is becoming accepted.
And that means that the adaptation an organism has to make because the environment changed causes for the environment the need to change as well. And then we have this cause and effect and cause and effect and cause. And then we have that feedback topic where you said you would like to tell us more on feedbacks, but there's so little time. So I would like to give you just a few minutes if you would like to add something.
Well, feedback is something, fascinating about complex systems, and the reason why they are so unpredictable. Because, first of all, we never know if the feedback which is activated in the dynamics of the system would be positive or would be negative. And I know I go to the point, I'm not a medical doctor, but I read about the struggle of medicine with things like cancer. And one thing that they observe is that certain forms of treatments work with some people, and the same treatment does not work for others. So of course, this is not my field of research, but when I hear or read about those stories, it makes me think about feedbacks. So obviously, for some reason that we don't understand, I don't understand, certain type of treatment to an illness, if it develops, for example, a negative feedback, then it balances. So it's able to stop the evolution, the growth of the disease, and cure the patient. However, for some reason that we also don't understand, if the opposite occurs and actually develops a positive or activates a positive feedback, so then there is this exponential growth of the disease and finally causing the death of the organism.
So can we set any rules for feedbacks?
Well,
like general rules for a certain system?
Again, depends on the type of systems. If they are very, very system, for example, a thermostat, that you can control the temperature in the environment, you can set a feedback mechanism that as the temperature hits a certain level, then they start cooling down to maintain that temperature and lower the temperature at a certain level, and then that feedback is disconnected. This is more a mechanical system. But usually when we look at living systems, the dynamics, the understanding of feedbacks operate becomes more difficult. So I'd say that systems thinkers are highly aware of the possibility of feedbacks, and therefore they know that any intervention, the result of any intervention is always uncertain. That's why there is less and less concern with things like prediction and control, because if I set up the initial condition of a system and make predictions, I'm assuming that I don't know if they are or not feedbacks, or if they are feedbacks, I assume that they are positive or negative, therefore I can predict the outcome. But if we don't know if there are feedbacks involved, if they will be positive or negative, it's very difficult to predict. This topic actually came out in our lecture here on planetary boundaries, that the scientists who study the planetary boundaries, one of the major concerns is about, they know that all these boundaries are interconnected, but this interconnectedness about these different processes at global scale will generate feedback mechanisms that we actually don't know. That is also another reason that everybody accepts the fact of, for example, global warming. But what is going to happen to a specific region, nobody knows. Okay, because again, the feedback mechanism that will be developed will be very much local. So it's as I said, a very fascinating topic by itself, could be discussed in a lot of contexts. But I think for this lecture here, I just want to bring this idea, this notion, and tell you that we always know the possibility of feedbacks. It's like thresholds, they are there. I don't know exactly how a system is going to respond to my intervention. By the way, again, I work in civic ecology. As I said, the experts act more as a facilitator as opposed to a technocrat. And the reason why he or she does that is to interact with the community in the intervention, sharing information in the two-way, provide information to them, receive information from them. And the goal is always to promote a positive change. So our hope here is that that process develops some type of self-organization through a positive feedback, and that intention of promoting that positive change grows exponentially and happens. But it's never certain. Maybe there is some type of a negative feedback. There is something that will not move the system in the direction we expect.
So actually, what we can say for systems in this, that they need to save their ability to adapt, and that is what you what you said also about complex adaptive systems. And there I would like to enter the topic with what you just mentioned with the facilitators. Facilitators try to make things easier, and then with the complex adaptive systems you were talking about complexity. So is that a possibility to reduce complexion in order to make the system handleable?
As again, the complex of a system increases a lot with the scale of the system under consideration. So when we are dealing with large scales, actually is impossible to reduce that complexity, because if we try to reduce, like, if I'm dealing with planetary boundaries and I try to investigate those at that regional scale, which would be a lot less complex, but that would run the danger of falling into a reductionism, because I could, for example, conduct small experiments on a small scale in which I could have greater control of the experimental conditions, and then come out with some conclusions, and then try to extrapolate that conclusion to the global scale. But as there is great danger in that process, because as you reduce complexity, you reduce the number of variables and drivers that affect the responsive dynamics of the system. So that means, and then when you try to extrapolate the behavior, you are consider that behavior as under the control of the same drivers of the small scale experiment. So therefore, there will be a lot of uncertainties, because there will be variables and drivers operate at the larger scale that were not part of the small scale experiment.
Okay, but that could be the only way to analyze a big system, doesn't it?
Well, I would say that depending on the scale of the system, like deal with planetary boundaries, we always are confronted at a very large scale, and we still have to handle it. Of course, we pay a price for that, because we cannot reduce it to have full understanding of it. Okay, so what's going to happen is we're going to know a little bit about it, and tremendous uncertainty about what you know. So, but this is an idea that systems thinkers live well with it, which is not a notion in that traditional orthodox science shares, because in orthodox science, the goal, the aim is total understanding, full understanding, is reducing uncertainty to a maximum, a minimum. So minimal uncertainty. So system thinkers know that is sometimes impossible, because the problem we are dealing with is so complex that we have no ways, no methods to fully understand that system. We can understand a little bit of it. So therefore, we have to accept, embrace, live with that tremendous uncertainty. In summary, to avoid to fall into the trap of reductionism, depend on the scale of the system being investigated, the complexity increases dramatically. So if I try to reduce that complexity to be able to fully understand it, I will be confronted with the problem of reductionism. So systems thinkers try to avoid that, but they pay a price.
Yeah.
They know that by understanding the large-scale complex system, they can understand a little bit. And that's why I think in the planetary boundary, I try to express the thinking of the scientists involved in that project, in that study, that although they think is conceptually sound, but obviously there is tremendous uncertainty about the interaction among those large-scale processes, which makes it difficult for policy making, for example, because there's too much uncertainty involved.
I would like to just ask one more question now that we should come to the end of this interview. Yeah. This complicated way of investigating systems is also shown in that problem you sketched when you said you cannot only look at the focal system, you also have to look at the, let's say, neighbor systems, like one bigger, one smaller. Maybe you can just tell us some short, or give us some short information on panarchy, on nestedness, and on integrated cycles, just to sum it up.
So again, panarchy, although Hollin and his associate used the name panarchy, but that is the same as network and nested hierarchies that systems thinkers use. So again, the idea is the same, that each system is in itself a whole and as a part of a larger system. Panarchy is the same idea. What is different is because Holland took an extra step to look at the dynamics of one particular system into that nested hierarchy, that each system within that hierarchy is cycling into those 4 phases.
Yeah.
So he takes, if I look at a system at a given moment, the system itself, according to his theory, is going through these 4 phases, which is within a larger system, which in itself is going through the 4 phases. So everything, all living systems, according to him, in each level that we look, is always going into this 4 phases. So this is one aspect. The other aspect that he shares about the need to always consider at least one scale immediately above and one immediately below, again, is the same idea of nested system. Because living systems are open systems. That means they are continuously interacting with the environment in which they live. And that interaction happens through the boundaries of that system consists of exchange of information, energy, and matter. So therefore, when I look at a system, a living system, which by definition is an open system, which implies that I always should look at that exchange because that exchange of information, matter, and energy affects its dynamics. So if I focus on the system itself and ignore the immediately above and the immediately below, I may miss that important transactions that is going across the scales. So I think what he is saying is that we should be aware of those transactions. And if you are dealing with living systems, open systems, we should be always have a way of considering something immediately above, something immediately below. That goes back to a question you asked previously, how much above we go again. As you go, levels and levels upon levels upon levels above, the focus becomes more and more complex.
Yeah.
So I think Holland is aware of this, and what he suggests is that at least use always 3 scales, one immediately above and one immediately below, to not miss one of these important interactions through the boundaries of the open system.
Because everything is connected, and that's what we already learned in the first lecture. And so you see that we find the issues from the very beginning now, and we hope to get that to an end and to have everything integrated again in that next lecture we do next week. For now, thank you very much, Professor Lopez, for the interview, and we'll see each other in lecture number 5.
My pleasure. Thank you.